Hello everybody. We are discussing today a part of heat and thermodynamics topic, that is transmission of heat. In fact, one question is expected from this particular chapter at Eamcet level, and transmission is possible in the case of heat in three different modes. One, of course, we know, that is thermal conduction, that is observed in metals, that means in solids. Whereas second one is thermal convection. That convection we find in liquids as well as in gases. And the third mode of transmission of heat is this, that is called radiation. This radiation in fact does not require any type of a material medium. Even through vacuum also, this heat energy can be transmitted in the form of radiation as such. And out of all the three, thermal conduction is the slowest and thermal radiation is the fastest processes. So this is the basic. While discussing about this chapter, few formulae first of all everybody should have in memory. One is the concept of thermal conduction, that in the sense conductivity of heat through a metal. In fact, the quantity of heat conducted through a metal rod or a metal cube, whatever the body be, that mainly depends on four factors. It's proportional to area of the faces across which the heat is transmitted, and it is directly proportional to the change in temperature across those two faces across which the thermal conduction that is taking place. Third one, it is directly proportional to the time of heating the first phase. What time we people are heating the first phase, depending on that only, the amount of heat energy will be reaching the other phase as well. Coming to the fourth one, it is inversely proportional to the distance of separation between the phases across which the conduction is taking place. If you club them all, you can write with a constant K, A, delta theta, that is theta 1 minus theta 2 into T by D. This is the equation. Out of that, K is called coefficient of thermal conductivity. That is actually the concept. Coefficient of thermal conductivity. This for a particular material it is going to be the same, and of course depending on the actual dimensions of that, we people is to calculate one. Coming to the second one, from this equation D by K into A, when I write like that, it is equal to theta 1 minus theta 2 into T whole divided by Q. This D by K into A, we call it as R, which is called thermal resistance. What is the application of this formula? Whenever that fellow says 2 or more number of cubes, or 2 or more number of blocks, or 2 or more number of rods which are made up of metals, they are all connected in series, then how to calculate the effective thermal resistance? R is equal to R1 plus R2 plus R3 and so on. Like that, when they are connected in parallel, 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3 and so on. Just like in the case of current electricity, what we have taken up while considering resistances connected in series and even in parallel. So this is the major equation one should remember. Now coming to the next one, that is regarding convection. Convectional energy, that is in the form of heat, that mainly depends on only two factors. One, of course, it's proportional to the area, and one, of course, is nothing other than the temperature over there. So if you club these two once again, Q is equal to a constant H into A into theta. This is what we call it as coefficient of convection as such. This is the point. What is the concept behind? When a cup of coffee is very hot, if a person wants to drink that one as early as possible or as fast as possible, then that fellow has to use a saucer there. What is the reason behind? More is the area, more will be the amount of heat that is going to be convected through to the surroundings. That is the concept. So that is one area you have to take up. And most important examples for convection are, one is the concept of a ventilator, that is based on the principle of convection. One is the concept of a chimney, in the case of an oil lamp or in the case of a factory, whatever we talk about, all these examples, they come under this convection part of it. Now come to the next one, that is about the radiation. In radiation, we have many number of concepts. In fact, we all have to take up the quantity of heat energy that is radiated per unit area per unit time. That is what is called Q by A into T. That is directly represented by E. That is the amount of energy emitted per unit area per unit time. That is equivalent to sigma into T power 4. This is the first formula, which in fact we call this one as Stephen's law. According to the Stephen's law, the quantity of heat energy that has been radiated by a black body per unit area per unit time is directly proportional to fourth power of its absolute temperature. So if you take that constant of proportionality as sigma there, E is equal to sigma T power 4. That is one equation which is called Stephen's law. But the point here is, whenever a body is losing energy in the form of radiation, not only the temperature of that body should be considered, but also we should take even the surrounding temperature as well. So this equation has been slightly modified by another personality. That fellow, of course, Stephen, along with him, Boltzmann. Both together have simply modified this equation. Sigma into T power 4 minus T naught to the power 4. What is this T over here? It is the temperature of the black body that has been taken, absolute value of temperature, no doubt. And what is this T naught here? That T naught is generally taken as the absolute temperature of the surrounding medium, or the medium in which we people are placing that black body as such. Suppose if it is not a black body, then how to just change this version? We people just have to take E is equal to, no doubt, Q by A into T is equal to sigma T power 4 into E we people used to write. This E is called emissivity of that particular body, which is not a black body in that particular case. If it is a black body, its emissivity is going to be 1. Therefore, you need not put this value of E anymore. That is 1. Therefore, you will be getting this equation as it is. So, based on these two formulae, there is a possibility for us to get a problem in the final Eamcet. That's one. Come to the next one, please. What exactly is the concept of Newton's law of cooling? In fact, we know the amount of heat that has been lost in unit time. That means the rate of cooling of a body, that is equivalent to K into theta 1 plus theta 2 by 2 minus theta naught. How to read this one? The rate of cooling of a body is directly proportional to the mean excess temperature of the body over its surroundings. That is the way we people used to write this equation. Theta 1 is the initial temperature, theta 2 is the final temperature. Theta 1 plus theta 2 by 2, that gives you the average value of temperature, that is also called mean value. This theta naught, we call it as the temperature of the surroundings. This average value, how much it is more when comparing to the surrounding temperature, depending on that factor, the rate of cooling of a body, that depends. So this is one more equation one has to remember here. Come to the next concept over here. We have Wien's displacement law also. Displacement law, what it says directly? This lambda corresponding to the maximum intensity of the emitted radiation is inversely proportional to the absolute temperature of that particular body. In other words, we can say lambda at maximum intensity into T is equal to a constant, like we people used to say. What is this constant usually be represented as? It is represented as B. That B we call it as Wien's constant. So this is what is called displacement law, which has been given by Wien. Therefore, we call this one Wien's displacement law as such. So these are the major formulae one has to remember before taking up some of the applications of this particular chapter as such. But all of you should understand the way we people used to change the version depending on that particular problem what has been provided to us. So let us start with the applications part of it, please. Let us check the very first problem. A cylindrical rod is with one end in a steam chamber and the other end in ice. It is found that 1 gram of ice melts per second. If the rod is replaced by another one of the same material but double the length and double the area of cross section, then the mass of ice melts per second will be how much? So the concept over here is cylindrical rod. You can identify directly taking this example. Here we are having one end connected to a steam chamber and the other end is now in a chamber consisting of some amount of ice. So whatever the amount of energy in the form of heat that is reaching from here to here, that will definitely be in the form of conduction. The amount of heat conducted from this end to this end will now be utilized by this ice to melt down there. So what exactly is the concept here? The heat energy required for this ice to melt is given by this particular steam chamber. That is, in other words, the amount of energy reaching over there is responsible for the melting of ice. What is that amount of energy? K A into theta 1 minus theta 2 into T by the value of L. This now must be equal to M into L. What is this value of M? Mass of ice that has been melted. And what is this L over here? Latent heat of ice. In fact, we all know that one has 80 calorie per gram and all. But in this particular case, he is comparing two different rods. See the dimensions of both the rods, please. First rod, of course, is melting 1 gram in 1 second. Fine. Now, what about the second rod? It is replaced by another one of the same material. Same material means what? Its value of coefficient of thermal conductivity is going to be constant for the second rod. But double the length and double the area of cross section. Length is doubling and area of cross section is doubling. We know steam is going to be at 100 degrees centigrade and ice is at 0 degrees centigrade. Therefore, the temperature difference remains constant in both the cases. And L is latent heat, which is 80. Always we know that is a constant over there. So what can we write from this one now? M by T, mass of ice melted per unit time, that is proportional to A by L. In other words, we can say M by T is proportional to R square by, that is A by L. Directly if you take the ratio like M by T of the first material, first rod by M by T of the second rod, that now is going to be A1 by A2 into L2 by L1. But of course, we people can understand A1 is okay. A2 is twice that of the first. And L1, if I take it in the denominator as it is, L2 is going to be 2 times the value of L1. So A1 gets cancelled, L1 gets cancelled, 2 gets cancelled. What is now left over? It's 1. Means what? M by T, that is mass of ice melted in the first case per unit time and mass of ice melted in the second case per unit time, both are equal. Both are equal means in the first case how much amount of ice that has been melted? 1 gram is melted. Therefore, even in the second case also you will be getting the same 1 gram. So M by T in the case of first one, in the case of second one, both are going to be same. So what should be our option now in this case? Third option is going to be the correct option for us because it is 1 gram that has been mentioned there and 1 gram only we people have got after calculating the value. So this is the concept one has to remember there. Now let us check the second problem, please. That problem says heat is flowing through two cylindrical rods of same material. The diameters of the rods are in the ratio 1:2 and their lengths in the ratio 2:1. If the temperature difference between their ends is same, then the ratio of amounts of heat conducted through them per unit time is going to be how much? Amount of heat conducted per unit time, that means the power, like we people can say Q is equal to K into A into theta 1 minus theta 2 into T by D or L. This is the formula. But he is talking about Q by T value. That means quantity of heat energy that is conducted per unit time he is asking. Heat is flowing through two cylindrical rods of the same material again. That means K remains constant. And what else he has given? Temperature difference between their ends is same. That means theta 1 minus theta 2 is again constant. What are the two other variables you are finding? One is area of cross section and one is the corresponding length. Then how to write this one? Q by T of the first material by Q by T of the second material, in the sense second body I am talking about. That must be equal to R1 square by R2 square into L2 by L1. That is the formula what we people can write. What is the ratio of diameters he has given? You see 1:2. Same will be the ratio of their radii also. So 1:2 whole square, 1:4. That is 1 by 4. Into lengths are in the ratio 2:1. That means now 1:2 I should write. It is 1 by 8 we are getting. That means what should be the correct option there? 1:8. That should be the correct option for us. So check that option number 4 once again. That is now going to be 1:8 as such. That is the concept. So fourth option is the correct option for us. Now look at the next question, that is question number 3. Two slabs A and B of equal areas are placed one over the other such that their surfaces are completely in contact. The thickness of slab A is twice that of B. Coefficient of thermal conductivity of slab A is twice that of B. The first surface of slab A is maintained at 100 degrees centigrade and the second surface of slab B is maintained at 25 degrees centigrade. The temperature at the contact of their surfaces will be how much? That is the concept. In fact, his concept is quite simple. He is just talking about two blocks which are being placed this way. One, of course, he is talking about A and other one he is talking about B. The thickness of this one, suppose if I take it as L, this is now 2L he has given. The thickness of A is twice that of B. And what is the temperature of this one? 100 degrees centigrade. What is the temperature of the other face of that B? 25 degrees centigrade. What is the temperature of their interface is the question. Another thing, if I take Ka, that is coefficient of thermal conductivity for the first material, that is given twice Kb. Now the question is, what is theta? Come on, just write. When the thermal equilibrium is taken up into consideration, Q by T is supposed to be constant across the system as such. That means what you should write now? Q by T means Ka into A into what is the temperature difference across A now? 100 minus theta. Right, divided by what is its length now? 2L is equal to Kb into area of cross section is same for both, right, into theta minus 25, that is the temperature difference, divided by L. But one thing you should understand, Ka is given twice Kb. That means if I write it twice 2 Kb here, Kb gets cancelled and you are left with 2 there. And L gets cancelled over here. This 2 gets cancelled, A gets cancelled. What is now left over? You check it. 100 minus theta is equal to theta minus 25. So 2 theta now becomes 125. Then what will be the value of theta now? 62.5 degrees centigrade should now be the temperature of the interface of that particular system. That means the second option is supposed to be correct for this case, please. So 62.5 is the option 2 for that question number 3. Let us check the next number. Fourth question. A wall has 2 layers A and B, each made of different material. Both the layers have the same thickness. The thermal conductivity of A is twice that of B. Under thermal equilibrium, the temperature difference across the wall is 42 degrees centigrade. The temperature difference across the layer A is how much? That is the concept. This model question has been asked several times in different entrance examinations, including Eamcet. That is one. So first and foremost, this is the wall what I am considering. And he is talking about A is one layer and B is the other layer. both are having the same thickness he has given. That means L over here is same in both the cases. That has been mentioned very clearly there. But what did he say? Ka, if I take, and Kb are the thermal conductivities of both the materials. It is again given Ka is equal to twice Kb. That is the relation. And if I take this theta 1, the temperature over here, theta 2, the temperature over there, theta, the temperature at the interface, then what is the value given there? Theta 1 minus theta 2 is given 42 degrees centigrade in the question. And what is this question officially? What is theta 1 minus theta? That is, what is the temperature difference across the first layer of that particular wall? That is the question what has been asked. And very clearly is mentioning under thermal equilibrium. What do you mean by thermal equilibrium? Once again, Q by T should be constant. When I write Q by T is constant like in the previous problem, Ka into A into theta 1 minus theta divided by this value of L. That is equal to Kb into area of cross section of the second layer into theta minus theta 2 by this value of L. So thicknesses are equal, areas of cross section are equal. Once again, he did not mention that the areas are different and so on like that. And another thing is Ka is equal to twice Kb. Then what will you get here? This gets cancelled and it will be 2 times. So what you can write? 2 times theta 1 minus theta is equal to theta minus theta 2. That is the equation ultimately what we are getting. Fine. Now carefully observe mathematical approach here. I add theta 1 minus theta on both sides. When I add that one, this automatically becomes 3 times theta 1 minus theta. And what happens to this one? Theta minus theta 2 plus theta 1 minus theta. I am adding the same value both sides. In this case, now theta getting cancelled, what will be left over? Theta 1 minus theta 2 will be left over. What is that value given over here? 42. Therefore, theta 1 minus theta, which is the temperature difference across the first layer, will now be 42 by 3. So how much it should now be? 14 degrees centigrade. See that option number 2 there, please. It is exactly given 14 degrees centigrade. So this kind of a problem is a very, very commonly asked model at Eamcet examination. So be thorough with this model, right? Let us check the next problem. Problem number 5. 2 hollow spheres of same thickness are filled with ice. The ratio of their diameters is 1:2. And the ratio of their thermal conductivity coefficients is 2:3. The ratio of times in which the ice gets melted in the 2 spheres is how much? Now he is giving you 2 spheres are taken up. Their radii are different. Radii are different means the amount of heat that ice whatever is taken in each sphere, that also differs. So we can understand directly in this particular case, ice should be melted. That means the quantity of heat energy, that of course whatever is just passing through, you can say Ka into theta 1 minus theta 2 into T by L. That now is going to be equal to M into L. But here if you carefully observe, he is talking about same thickness. Therefore, no need for you to take this L into consideration. And anyhow this L is constant, that is latent heat we know. But how to write this M now? 4 by 3 pi r cube into rho I can write. In fact, you know this one very well. This is actually the concept of 4 by 3 pi r cube when I take up. It is the volume into density that is going to be the mass part of it here. Right? And his question is, what about the time? And what this A to be written now here? It is 4 pi r square I should write. Because that is the surface area of the sphere. Then what you will get in this case? 4 pi is constant here. 4 by 3 pi here constant. Rho is going to be constant. R square cancels here r times. Then what can we write now directly? T in this case is proportional to this R by K into R by K, direct. That means what are the values he has given you? See, T1 by T2 is equal to R1 by R2 into K2 by K1. Direct application. K1 is to K2 is given over here. That is 2 is to 3, 3 is to 2 it becomes. R1 is to R2 that is given. 1 is to 2 that of course. If you substitute the values, look at those options once again. It is 3 is to 4 given, 4 is to 3. Check that key over there please. That is exactly 3 is to 4 you will be getting like. So this is actually the concept. This is 1 by 2, 3 by 2. Directly you will be getting 3 is to 4. There is no other calculation that is needed here. 1 by 2 and this one is 3 by 2. So that is actually the concept. T1 is to T2 must now be 3 is to 4. So that is the question number 5. Let us check the next number please. Question number 6. 3 rods made of same material having the same cross section and lengths are joined as shown. The temperature of the junction of the rods will be how much? This question also has been taken from the previous Eamcet papers. If you just look at the rods of the same length are placed this way now. This is mentioned 0 degrees centigrade. This is given 90 degrees centigrade. This is also given 90 degrees centigrade. But one thing you should understand well, if I take the temperature over here as theta, these two are at higher temperatures, then naturally the temperature should now come this way, the heat energy should move this way, and both used to enter into this. From higher temperature side to lower temperature side, generally the heat is going to flow. We know that point very well. Now, in this particular case, since all the 3 are having the same material, K value will be the same, their lengths are equal, areas of cross sections are equal, only variable you are finding over there is the temperature difference, nothing more. So, what we should write the temperature difference here? 90 minus theta. That is the temperature difference across this. Same is the value for this also. So, into 2 I write it. So, the temperature difference here is 90 minus theta, here also is 90 minus theta. So, total put together 2 into 90 minus theta, that now should be equal to theta minus 0, that is simply theta. So, you can write 180 must be equal to 3 theta. Then what will be the value of theta over here please? 60 degrees centigrade. Look at those options once again, 45, 60, 30 and 20. So second option which is 60 degrees centigrade here is supposed to be the correct option for us in this particular question number 6. Let us check the next problem, that is problem number 7. A cylinder of radius r made of a material of thermal conductivity K1 is surrounded by another cylindrical shell of inner radius r and outer radius 2r made of material of thermal conductivity K2. The ends of the combined system are maintained at 2 different temperatures. There is no loss of heat across the cylindrical surface and the system is in steady state. That means it is perfectly in equilibrium, thermal equilibrium as such. The effective thermal conductivity coefficient of the system is how much? Effective thermal conductivity, even this question has been taken from previous Eamcet papers. If you look at carefully, he is just talking about 2 cylinders. One cylinder is taken this way, it is a solid one, fine. Another one is simply a shell. Shell is now covering this much of area like. That means what you people can find is its internal radius is its external radius. The total radius over here is given as 2r. That is what has been given in the problem as such. Now, in such cases, remember carefully, K into A should be constant. That is the simplest way of remembering the formula. You need not write K into A into theta 1 minus theta 2 into T by L because all other things remaining constant. K into A is constant here. In other words, you can write K into R square will be constant. What for you can understand, A is going to be pi r square like cross section. If you take that area there, it is pi r k r square like. Now in this particular case, how to write that? K effective, that is what we want, into what is the total radius over here? 2r whole square is equal to, what is the thermal conductivity of the first one please? K1. What is its radius now? R square. Plus, what is the thermal conductivity of the second one please? It is no doubt K2. But what is R square for this? It is 2R whole square minus r square. That is the concept. Why? Because only this much of portion you people are finding as the external cylindrical shell there. Therefore, how much its value will be now? 4r square minus r square, that now becomes 3r square. So, k1 into r square plus 3k2 into r square is equal to k effective into 4r square. Throughout this equation, r square you can cancel that one. So, what will be the value of effective k value here? k1 plus 3k2 by 4. Just look at this option there. k1 plus 3k2 by 4. That means the third option must be the correct option for this question number 7. k1 plus 3k2 by 4, that is now going to be the effective thermal conductivity coefficient of the system as such. Remember this type of a formula for this model question, please remember. Now let us check the next question, that is problem number 8. Two black bodies at 327 degrees centigrade and 627 degrees centigrade are suspended in an environment at 27 degrees centigrade. Environment 27 degrees means what? That is the temperature of the surroundings of these two black bodies, whatever he is describing there in the problem. The ratio of their emissive powers. In fact, we all know well, emissive power if you take up, is it not equal to sigma into T power 4 minus T naught to the power 4 according to Stephen Boltzmann law. So now in this case, you can write E1 by E2 is equal to T power 4, 327 degrees centigrade. You have to add 273 to it. That now becomes 600 to the power 4. 627 degrees centigrade, that is as well equivalent to 900, that is, so 27 degrees centigrade is the surrounding temperature, plus 273, that means 300 whole power 4, divided by what is the temperature of the second body? 900 to the power 4 minus 300 to the power 4. Seeing this calculation, one need not become panic. We can directly understand to the power 4 when you take here 8 zeros, here 8 zeros, 8 zeros here also. They all get cancelled. So, how to write this one now? 6 square whole square. That is 36 whole square. I can write this. 6 into 6 into 6 into 6. 36 whole square. Minus 3 square. That is 9 whole square. I can write 9 square. By this one is 81 whole square. This one is again 9 whole square. Now you can directly apply a square minus b square formula. A plus b, it is 45 into a minus b, right? 36 minus this 9, that in the sense it is 27, right? Now in this particular case, next one, 81 plus 9, it will now become 90, and 81 minus 9, 72 as such. Look at now, this goes exactly twice. 9 times 3 and around 24 times 3. Once again 3 times 3, again 8 times 3. So what is now left over? 3 is to 16. Look at that option where it is. It is now given the third option 3 is to 16. Don't be once again confused by looking to the second one 16 is to 3. It is not the correct order. The correct order says it should be 3 is to 16 only. So correct answer is going to be the third option for us. Now look at the next number, that is question number 9. Two bodies of same shape and size having same radiating power have emissivities 0.2 and 0.8 respectively. Ratio of their temperatures will be how much? That is the concept. Emissivity whenever is given, I have already mentioned in the beginning itself, sigma T power 4 into E we people used to take. That E for a black body, perfect black body, its value is 1, therefore we need not mention that letter E anymore for a black body as such. Here he is talking two separate bodies. Then when that fellow is telling their emissive powers are 0.2 and 0.8 and the power is going to be the same, E is same, sigma same, then E is inversely proportional to T power 4. In other words, you can write the same. T1 by T2 is equal to E2 by E1 whole power 1 by 4. Now what is E2 given? 0.8. by 0.2 to the power 1 by 4. This of course gets cancelled 4 times, fine. But 1 by 4, can't you write 4 to the power half whole power half directly? This is nothing other than root 4 whole power half. What is root 4 here? It is 2. That means that is 2 to the power half again. Is it not root 2, please? So what should be the ratio there, please? Root 2 is to 1. That must be the second option for this particular question number 9. Okay, so emissivities, whenever the values are given up, you just have to take this formula for the relation between E1 and E2 respectively. Look at the next problem, that is problem number 10. A black body at a temperature 400 Kelvin placed in an enclosure 300 Kelvin has cooling rate as R. If the temperature of the body were 800 Kelvin and placed in the same enclosure, the cooling rate is approximately how much? That is the concept. Again, you have to think of the same radiating power, nothing else in this particular case. E1 by E2. When I write this one, T1 to the power 4 minus T0 to the power 4 divided by T2 to the power 4 minus T0 to the power 4. First value that has been given over here is 400 to the power 4 minus, what is the value of enclosure given? 300 to the power 4 by 800 to the power 4 minus 300 to the power 4. As I said earlier, all zeros they get cancelled even after taking the fourth power as well. This now becomes 16 square minus 9 square by this 64 square minus 9 square. Directly you take this value once again, a plus b into a minus b, 25 into 7. Right, divided by 64 plus 9, it is now going to be 73, right, into 64 minus 9, that is going to be 55. So what exactly the value you people are going to get here? This is 25, roughly if you take, for example, it goes 3 times like. So what you will be getting around 25 into 7 is going to be 175. That divided by this total value, the ratio itself we people can take up. This value E1 is given as R and E2 to be calculated. What is E2 now? 73 into 55 divided by into R by 25 into 7. Roughly you check it. This goes twice here. This goes 10 times there. 20. 20, it's going to be a little more than 20. What are the options given? 23R is suitable answer for this. What for? You need not calculate the entire thing. Roughly you do it. 25 goes in 73 nearly 3 times. 7 goes in that particular case like you can think of. It will be around 20 and above 20. There is only one option that is nearby 20. That's now going to be 23R. So third option is the correct option for this question number 10 as such. Let us check the very next one, please. 11th one. The radiation emitted by a star A is 10,000 times that of the sun. If the surface temperature of the sun and the star A are 6,000 Kelvin and 2,000 Kelvin respectively, the ratio of radii of the star A and the sun is how much? That is the concept. Look at carefully emissive power he is talking about. How many times the radiation of star A? 10,000 times that of the sun. So you can understand E is equal to actually Q by A into T. This in other words, power by area of cross section I can take up. So what is this power? Power now? Power is equal to sigma T power 4 into the value of A as such. But what are the values he has given you? And he has not mentioned any emissivity there. So no need for us to take that value anymore now. So what is his question here? P of the star by P of the sun, if I take, that is equal to T of the star whole power 4 by T of the sun whole power 4 into radius of the star by square by radius of the sun square. This is the formula. What is the ratio of radii is the question he is asking you. So let us take P of star A is 10,000 times that of the sun. So simply write 10,000 into P of the sun. Then automatically this P of the sun in the denominator and this one they get cancelled. Fine. What is the temperature of the star given? Sun is given 6,000. So 6,000 here and here 2,000 whole to the whole power 4 into R star square, right, by R sun square. That is the formula actually we have to take. Now 3 zeros they get cancelled and this gets cancelled thrice. 1 by 3 whole power 4. Is it not 1 by 81 please? So what will you get now? R of the star whole square by R of the sun. If you take whole square, that now becomes 81 into 10 to the power 4. Then what will be the ratio? R star is to R sun. If you take, what will be that value now? Root of this 900 is to 1. So just look at that ratio please. 900 is to 1 is supposed to be the ratio which is supposed to be the third option for this particular question number 11 as such. Right? Now check the next one, that is question number 12. Two electric bulbs have filaments of lengths L and 2L, diameters 2D and D, and emissivities 3E and 4E respectively. If their temperatures are in the ratio 2:3, ratio of their powers will be how much? Once again, take up the same formula for power as such. But in addition to this, emissivity also should be taken up. So sigma is anyhow constant we know. So we can write P1 by P2 is equal to T1 by T2 whole power 4. That is one area you have to take up. What are the temperature ratio he has given? What is the temperature ratio? 2:3. And what is the next one he has given you? Diameters are given. That means this can be taken R1 square by R2 square. But it is not cross-sectional area. Understand this point carefully. What is A now to be taken here? 2 pi R into the length of it. That is the total surface area of a cylinder. So what to write in this particular equation carefully you observe now. It is to be taken R1L1 by R2L2. That into E1 by E2. That is the final formula. Don't be mistaken, this is not area of cross section. It is the surface area of the filament in each of the bulbs. That is the point. Now if you take T1 by T2, it's 2 by 3 whole power 4. That is 1. Into what are the radii he has given you? One is 2D and one is D. Fine. What about their lengths he has given? One is L and one is 2L. Excellent. Then what is the ratio of E and E values? 3E and this one is 4E. Directly you cut this L here, right? 2 here, D here, E here, straight away. So what is left in this particular case? 4 4 the 16, 9 9 the 81 into 3 by 4. This anyhow goes 4 times over there. This goes 27 times over here. Look at that ratio now. It should be 4:27. See that option number 2 there carefully. It should be 4:27. This is the way. Only point one has to remember in this case is LA is nothing other than the surface area of the that particular filament, which is 2 pi r times its length we people is to take up. Look at the next number, that is problem number 13. Two hot copper spheres of radii in the ratio 2:3 are kept in an evacuated enclosure. If each sphere is initially at a temperature 10 degrees centigrade above that of the enclosure, the rates of loss of heat of the spheres will be. In fact, rate of loss of heat, that is Q by T, we just want. In fact, in this particular case, Q by T is proportional to R square. That is the simplest way, because Q by T should be proportional to A. A of course 4 pi R square for a sphere. You can directly write R square. Then what will be this ratio? Q by T of the first body by Q by T of the second body must now be equal to R1 square by R2 square. What is R1 R2 ratio given? 2 square 4, 3 square 9. Then automatically what should be the correct option over here, please? 4:9 must be the correct option, which should be the very first option in this particular question number 13. That is the concept. Look at the next one, that is question number 14, please. The rate of emission of a black body at temperature 27 degrees centigrade is E1. 27 degrees centigrade means, you can understand, it is 300 Kelvin. Yet this much of temperature, the emissive power of that black body is given as E1. If its temperature is increased to 327 degrees centigrade, that means it will now become 600 Kelvin. Its value is given as E2. Now the question is, what is the relation between E1 and E2? Simple concept. E1 by E2 is equal to 300 by 600 whole power 4. E is proportional to T to the power 4 is the formula. This goes twice. So 1 by 2 whole power 4 now becomes 1 by 16. So what should be E2 now, please? 16 times the value of E1. This is the relation between E1 and E2 as such. Look at E2 is equal to 16. E1 means the very second option that is going to be tallied according to our calculation for this question number 14. Look at the next one, please. Question 15. The temperature of a black body is increased by 50%. Then the percentage increase of its radiation is approximately how much? In fact, this can be solved by taking the concept of E is proportional to T power 4. Take initial temperature as 100. Write this equation as it is. Take this as the first equation. Now when it is increased by 50%, then you can automatically write this becomes 150 whole power 4. And you can write this one as E plus X. That X is now going to be the corresponding increasement in the percentage in the radiated amount of energy. Now you write E plus X by E. In other terms, we can write this one as 1 plus X by E. It is 150 whole power 4 by 100 whole power 4. This of course you can write 3 by 2 to the power 4. 3 by 2 to the power 4 means after all how much that is going to be? 81 by 16. I just want X by E value. What will be X by E now? 81 by 16 minus 1. That is 81 minus 16 by 16. You can definitely understand 80 minus 16 is going to be 64. Plus 1, 65 by 16. I want percentage. Then automatically how much it comes to be? Around 406% you will be getting. But what are the options given? Approximately, that is the question given. So 400% is supposed to be the correct option for us. That means the third option is going to be the correct option for this question number 15. Right? Let us check the next number, that is number 17. Same, almost same model, but a different concept here is involved. A body takes 4 minutes to cool from 100 to 70. If room temperature is 15 degrees centigrade, then the time taken by it to cool from 70 to 40 is nearly how much? Once again, let us check the same equations for this question as well. It is 4 minutes to cool from 100 to 70. 100 minus 70, it is 30 by how much time it is taking? 4 minutes is equal to K into 100 plus 70 by 2, 170 by 2 minus what is the temperature of the surroundings given? 15. Second equation, what is the thing? 70 to 40. Again the difference is 30 by what is the time taken we just want? Is equal to K into 70 plus 30, 100 by 2, right? Minus 15. Simplify this one directly. 30 goes off. T by 4 you will be getting. This by this. K gets cancelled. 170 by 2 is going to be 85. 85 minus 15, it's going to be 70. Divided by, this is 50 minus 15, right? It's going to be 35. So directly you can understand here in this particular case, what is this value you are going to get? So what will be the value of T here, that is the concept here. So if you take this value of T by simplifying the first and second equations directly, you will be getting T value nearly 7 minutes. In the sense what? It is nearly, that exactly the concept. Fourth option is supposed to be correct over here, please. So the value of T in this particular case will now be exactly 7 minutes of this particular calculation as such. Look at that concept carefully. One of the excellent questions and very important models for this particular chapter. Check that next one, please. Problem number 18. A calorimeter of water equivalent 6 gram has 64 gram of water. Another identical calorimeter has a liquid of mass 50 gram and specific heat 0.6 calorie per gram per degree centigrade up to the same level. That means their volumes are equal. If both of them are allowed to cool in the same surroundings through the same range of temperature and the time taken for water to cool is 140 seconds, the time taken for the liquid to cool down is how much? That is the concept. Now here you can understand the powers are going to be equal. That means what? You can say ms delta T, right, of the calorimeter plus ms delta T of water whole divided by time, that means total power, that must be equal to ms delta T of the calorimeter, this time ms delta T of that liquid whole over the time. Here it is T1, here it is T2. Now what is ms of the calorimeter given? You check that one. Water equivalent of 6 gram. So directly you can take it for granted that the value of water equivalent over here is 6. Delta T is same in all the cases. So no need for us to take that one. Plus what is the mass of water that has been given? 64 and specific heat is 1 by T1 must be equal to, what is ms of calorimeter again? 6. What is mass of the liquid that has been mentioned over there, please? 50 gram. And what is its specific heat given? 0.6 by T2. But if you just look at the problem carefully, T1 is given 140 seconds. That is the point. So you can understand this now becomes 70 by 140 is equal to this 0 and this point, they get cancelled. 6 5 the 30. 36 by T2. This actually is the value, this goes twice. So T2 must be exactly 72 seconds or whatever the time that has been mentioned there. 72 seconds we just have to get for the liquid as such. So correct option for this one is the question number 1, please. Look at that option number 1. Look at the next number, that is question number 19. A star behaves like a perfect black body emitting radiant energy. The ratio of radiant energy per second by this star to that emitted by another star having 8 times the radius of the former but having 1/4 the temperature of the former will be how much? That is the concept. Once again, emitted energy we just want E is proportional to T power 4 into R square. That is the point. So what can we write now? E1 by E2 is equal to T1 by T2 whole power 4 into R1 by R2 whole square, like we can take. The temperature 1 you take it as it is. What is the temperature of the second one he has given you? 1/4 the temperature. So T1 by 4, 4 goes up and this is to the power 4. Fine. What about radius he has given? 8 times the radius of the former. That in the sense what? R1 if I take it as it is, this R2 is going to be 8 times R1. That is the concept. So simplify this one, this gets cancelled, this gets cancelled. You are now getting 16 into 16 here. By here 8 into 8. Because 8 square we people are getting directly there. So this goes twice and twice. So 4:1 should now be the correct option for us. That in the sense the third option will now be the correct one for this question, please. Look at the next number, that is question number 20. The wavelength corresponding to maximum intensity of radiation emitted by a star is 289.8 nanometer. The intensity of radiation for the star is how much? given Stephen's constant and Wien's constant. So this is a direct application of Wien's displacement law first of all. You can understand lambda minimum into absolute temperature is equal to B, which is called Wien's constant as such. So what can we write now? T is equal to B by the lambda corresponding to the maximum value. So what will be the value of B over here given? 2.9 into 10 to the power 3. Directly of course it has been given minus 3 over here by what this lambda given? 289.8 nano, that means 10 power minus 9. You will be getting the value of capital T over here. But what is the question he is asking you? He is asking E now. E is equal to sigma into T to the power 4. That sigma is 5.67 into 10 to the power minus 8. That into this value of T, whatever you are getting, that to the power 4. If you simplify this one, you will be getting around 10 power minus 4. That value 10 power 4 you will be getting. So 10 power 4 whole power 4, it will be 10 power 16. So 5.67 into 10 power minus 8 into 10 to the power 16. This gets cancelled 8 times. So what will be left over now? The very first option, 5.67 into 10 to the power 8. This must be the correct option for us. In fact, watt per meter square will now be the corresponding unit over here, please. So what will be this value? You will be getting around 10 to the power 4 you will be getting. That only we have substituted over here. That value of course coincides with the very first option in this particular question, please. So if you are a little careful with this particular chapter, transmission of heat as such, surely every one of you can take up 1 mark in the final examination. The general calculations are looking a little lengthy, but those calculations can definitely be made easier while taking up mathematical approach over there. So these are the concepts what are to be taken up as far as your first year intermediate syllabus, the last chapter that is concerned, please. So likely we may be having in the next few sessions, in the forthcoming sessions and all, we will be having the second year syllabus starting from wave motion and other topics as well, right? So these are the things we people are having for today. Thank you.